Good afternoon and all. Thank you for joining us for today's session for this exciting active online talks of episode 103. An introduction to natural. I am delighted to host for this knowledgeable packaged session. Creative. Creative is a group of people who are like-minded and curious to gain new knowledge. Active. Cre means creativity. Active means to be active. Activeness. To be active, we need creativity. Knowledge Square is our tagline. Sharing of knowledge increases our knowledge. The vision of Creative is to build constructive thinking on various domains. Our main focus on non-textual, non-academic, non-syllabus related concept. Every Saturday, we organize online weekend talks on the Zoom platform and we live stream our program on our YouTube channel, Creative GBD. Creative is thankful to all our resource persons for engaging us with their knowledge. Nanomaterials in modern science. Nanotechnology has emerged as a game changer in various scientific disciplines, revolutionized industries, and opening up new possibilities for technological advancement. Nanomaterials, with their unique properties and vast potential, plays a vital role in their innovations. As we progress through this talk, we will witness the impact of nanomaterials and on diverse sectors and how they have transformed the landscape of modern science. Before start this session, let us welcome our eminent speaker, Dr. Gopal Krishna Hegde, sir. Welcome you, sir. And I call Divya, creative volunteer, to introduce today's speaker.
No, I think no need. Let me start. I will introduce myself. Okay.
Okay, thank you, sir. You can proceed, sir.
Fine. Okay.
Okay.
Hello. Good afternoon.
Yes, sir.
1 minute. I'm just. Hello. Can you hear me?
Yes, sir. Yes, sir.
Okay. Okay. Good afternoon. I'm Gopal Krishna Hegde from my Indian Institute of Science, Bangalore. So I'm trained in physics, but I work in various research fields, mainly on nanotechnology, photonics, and different fields added together, and various applications of this nanotechnology and photonics. So because we are in the age of AC means after Corona. So though I don't like to give these online talks because I don't see anybody, but it's the way of life now. We have to, whenever so it's necessary and somebody asks, we'll go for these online talks. So I feel that I'm talking to myself because I cannot see anybody. And as the information is given to me, students from undergrad, BS, BE, BTech maybe, and master's students are sitting here. Assuming that different background people are sitting, I'm trying to make it as simple how the science and engineering in this area is moving forward. So that's what the whole idea is. Okay, I'm not going to hardcore mathematics or derivation or these kind of things. Just a talk on the technology perspective, hoping that it will reach you. Okay, so this introduction to nanotechnology, the title I picked up. So I've been working in this area for last 10-15 years. Why this nano? First of all, let us go with this. My talk is arranged in this way. Brief introduction to nanotechnology, then conventional and advanced techniques to make this nano devices or nano materials, and bottom-up methods where anybody can try and what we can take, because that is very important. And the summary, what we can take means, so we have been talking all these higher end technologies, but we will be, just talking and we will not be able to make our own products out of it. We do a lot of research and we cannot take it further. That is always a problem in these kind of technologies. Okay. Now, what is this nano? Nano means, I hope you can see the screen. Hello? No response?
Sir, audible, sir.
Audio and visible, the screen is?
Yes, sir. Yes, sir.
Okay. So this is nothing but dimensional scaling. So from the emergence of quantum mechanics in 1905 and on, so people are thinking how to reduce the dimension of the material. If I have simple metal, say copper, aluminum, whatever it is, we have the aluminum rod, and I can reduce the dimension such that it goes from centimeter to millimeter to micrometer from this side, from the upper side, from centimeter to meter, kilometer. That is a level. So this is a downscaling from the smaller size. So when the property of any material for that matter, that changes if its dimension is reduced of the order of 10th scale. So here some image is given here. This I'm talking about 1 angstrom. That is about 100,000 femtometers. Okay. So that's what the numbers. I hope you all get these numbers. Okay. Micro means 10 to the power minus 6 meters. Milli, okay, minus 3. Okay. Centimeter to 10th order down, like that. So micrometers to nanometers, the 10 to the power 9 meters. Okay. So this is where the scaling comes. So from the development of semiconductors, that means in 1960s, when these silicon-based semiconductors are now invented, and when the diodes and transistors are made using the semiconductors, the dimensional scaling started. Maybe by 1980s, we started getting integrated chips, IC chips and all. That means on a semiconductor wafer, hundreds of thousands of transistors are integrated. So that is called the integrated devices started coming. So here, if you look at, this is an image of an atom. And if you look at on the right side, the nucleus, proton, neutron, and electron. And the dimensional scaling, if you go nanometers to below picometers to femtometers, you are hitting an atom scale. Atom, see, that means I can, so a generic atomic planary model, this is a model, okay, size of 1 angstrom, then I can say one atom, the diameter of one atom is roughly about 1.1 nanometer. Now, if you look at this one, graphene nano ribbon thickness is about 1 nanometer. The same, that's the single wall, the same sheet is, if it is made into a tube, it is called carbon nanotube. This is about 10 nanometer. This is multi-wall research, 100 nanometers. See, why I'm talking the nano, the word nano started with the materials when the carbon, okay, the graphene is formed, okay, carbon nanotubes, carbon, this one that is motivating the scientists. Is it possible to make all these materials, particularly semiconductor materials, of this scale? So why? Because if the materials dimension is reduced, their properties are drastically changing, like physical properties, chemical properties, optical, mechanical, electronic properties, all change. This now leads to more invention to explore these things for various applications. Why? Because the semiconductor technology in 1980s started miniaturization and integration of many functionalization methodologies to do so many things. as a function. Like, in computers, you see memories and, memory chips and processors and various types of sensors all came up because of this miniaturization. So that motivated to look below that. Now, if you look at the day-to-day life, what we can see is this Gedeno nanorods. It's another, nanoscale material that is, that is started in 19 or 2000 above. And see, that's a different method I will show you later. And this is about 1 micron. Then human red blood cells, it is of the size 8 to 10 microns. Same thing, microelectromechanical systems. That means this is as device fabricated on silicon. So it's called a tweezers. It's a mechanical tweezers. And this is being used to hold the individual cells, the biological cells. See, it is very difficult to handle them. So the cells normally fold. So if you want to hold the cells in a normal planar condition, you can use these tweezers. This is called a microelectromechanical system. This is about 150 microns. I can control the movement of this tweezer tip by applying voltage on the backside. So this is what this is a micron scale technology. Okay. So still, if you go like this, these are the repeated, nothing to worry, shapes of this single wall carbon nanotube, a sheet of, this is all 0.1 nanometer, 10 nanometer, 100 nanometers. Okay. Now, so this is what I'm trying to stress here. Okay. Okay. So this is the first, I can say, first production of nanotechnology based product, that is carbon nanotubes. Okay, if you look at the right side, that means I mentioned if the material's dimension is reduced drastically, the physical, chemical, and various properties will change. So one of the glimpse of this is a carbon nanotube. These materials are available in India also. This test tube you can see here, depending upon the size of the carbon nanotube, the fluorescence of the material is changing. The fluorescence emission of this, the color, you can say the wavelength depends on the size. That's what the optical property is drastically changing. Okay. Now, various techniques have been developed to produce nanotubes in sizable quantities, including arc discharge, laser ablation, high pressure. Okay. All this, why I'm talking about how to make this research challenge all these years. Now, many of these techniques have been matured so that you can make this nanostructure on a big scale. That was a bottleneck for some years. I think in some applications these are well established. So I can see this on the left side. You can see this is a carbon nanotube. It is commercially available, and scientifically, if you centrifuge and see the fluorescent properties are different. So this is same material, but the dimensional scale. Okay, this is smaller. See, that is segregating at the top. Red color it is emitting. Okay, bluish. This is pink color. So all different fluorescence. Now, why nanotechnology has the potential to change every part of our lives? Nanotechnology affects all materials, metals, ceramics, and biomaterials. This is what an interesting property here, because when the miniaturization or dimensional scaling of materials started, that was started with silicon only. So silicon, now after so much of research and all, nanotechnology can be done with even ceramics, metals, polymers, and biomaterials. So this is more of interdisciplinary. Okay, new materials are the foundation of major technological advances. In the coming decade, nanotechnology will have an enormous impact. Okay, nanotechnology may be able to create many materials and devices with vast range of applications: electronics, medicine, biomaterials, energy production, and agriculture, environment, and so on. So this is what the future technologies which play a key role in our lives, and also they definitely contribute to the economy of the country. That is important. Okay, so nanoelectronics is one hot field. You all know the semiconductor technology has come to a stage where you cannot integrate more transistors. Okay, 1 billion transistor in 1 square centimeter dimension. But now, because of various other physics, you cannot accommodate more and more. Then the next stage will be nanotechnology. That means you have crossed the limit of the micron scale technology, where the physical properties will be different. There will be other various physical, electronics, optical property limitations. So mainly nanoelectronics, information technology, communication technology, making various technology redundant, leading to application which could not have been developed, even thought about without this new approach. So this limit can be crossed if you master this nanotechnology. Okay, materials of this size display unusual physical, chemical, optical, mechanical, electronic properties caused by many factors, including the increase in surface area compared to the volume. That is a very important property of this one. Okay, surface area is larger compared to its volume, which occurs as the particles get smaller. With this key point, there are various methods, various technologies are coming up. Okay, that means the take home of this part is, what is nano? Nano means just materials, dimensional scaling, and you will see very unusual properties of the materials. So as I mentioned, even metals, ceramics, and polymers all can be used. And with this, what it can do? Okay, like it's already being applied in medicine, diagnostics, sensors, drug delivery, tissue engineering. Okay, see, like in diagnostics, varieties of nanosensors are being used. Okay, drug delivery can be done through gold nanoparticles, silver nanoparticles are coated with drugs, and they can be controlled, they can be put into your nerve system, and it will go to the point of care methodology. We can deliver the drug at a desired location. Okay, like environment filtration and varieties of sensors are available, and you can detect anything through drones and very high quality nano sensors. You can predict the diseases of the crops well in advance, like reduction in the energy part, reduction of energy consumption, increasing the efficiency of energy production. Okay, information and communication. See, memory storage, novel semiconductor device, optoelectronics devices, they're all very important for communication, displays, quantum computers. So there is no end to it, because the quantum computer is a very interesting area, and India is also spending a lot of money to develop quantum computers. Okay, I think this itself is a separate topic to be covered in maybe one of your talks. Okay, so then heavy industry like aerospace, construction, glass coating, varieties of applications you can see. Vehicle manufacturers, I think you all know these days, all the cars and vehicles are put up with MEMS, micro electromechanical based sensors. All cars are having this kind of sensors. Now, next generation, you will have nanotechnology based sensors. These MEMS technologies have been invented around 20 years back. Now they are all well established, and we are using all those things. So it may take some more time, like consumer goods, nano foods, household, optics, textile, cosmetics, agriculture, okay, and sports. These are the possibilities, and many have been already deployed in applications. And still, one thing we have to remember: risk of using nanoparticles in construction, and also the risk of disposing the nanoparticles, nanomaterials, still a big challenge, because we have been experiencing the computer user computer wastages. These are still a problem to dispose, where to throw it off. Okay, all countries are facing the same problem of disposing now the laptop era, and all bulky computers, TVs, you don't know where to dump. So this risk is always there. Even for nanotechnology, it may be causing still hazardous health mainly and environmental disasters. So though that is a big question you have to keep in mind before doing any advanced technology. Now, see, this is a micro electromechanical systems in sports. I think it's already there. I'm showing something which is a very old, maybe around 2005 when I was running a marathon. This is the technology. I think that time itself, they started. You can see this marathon runners were using a sensor. It is tied to their legs. Okay, this is me. I'm running here. And I was in Singapore. This is the sensor. It's called micro opto electromechanical based sensor. And you can see this is an international marathon. At a time, there will be 25,000-30,000 athletes running. So it is very difficult to keep the track of who started first when they are completing. This is around 43 kilometers run. Now, each participant is given with a sensor. They have to tie to their shoelace. Okay, so you have to register for the run. And I think now, I don't know, now last 10 years I didn't run for this kind of marathons. I don't know, they are still having, because that time itself, this is a photo which I took from the web, that time itself, from the website, because these 25,000 people all will be having sensors in their legs. The whole entire running history will be recorded on the camera, and the counting will start. See, wherever you cross, your time is recorded. Every 2 minutes, there will be a sensor. You are crossing that sensor. It's a laser-based sensor. So this is what the technology is, okay? So, okay, this one more you can see. Like that, you can see. Now, it's a multidisciplinary science. Like one of the Indian art form, why I'm talking about this one is nanotechnology is more multidisciplinary. There is no, see, when the semiconductor technology started, it was mainly limited to physicists and electronics, maybe electrical engineering, to some extent mechanical engineering for packaging of the chips. Others of multiple, no biology people were aware of this one, and like chemistry. No, even the chemistry is more involved there. Not much. It was like a limited to this. Now, nanotechnology is multidisciplinary. So anybody can, even biology, medical people, are all working using nanotechnology left and right. It is like one of the Indian art form, like Yakshagana, one of the coastal Karnataka. So this you can see here, this is a multidisciplinary art. So all art is involved in this. You can see music, classical music. You can see dance, costumes, dress, the story, and whatnot. This one profound discussion, knowledge, and depiction of Indian epics, Ramayana, Mahabharata. So entered, say, like nanotechnology is in a similar state. Okay, I'm just comparing that way. Now, if you look at this one, if you scale down, what I'm talking about is nano. Still, you can go pico, 10 to the power minus 12. So if you reach around 10 to the power minus 15 femto, so you can have the materials, or like one gear system is shown here. This is made up of individual atoms. Okay, can you imagine that one? If you look at the left side, MEMS, micro electromechanical based gas system. So this is a device fabricated on silicon. This gas system, it's a 2D, two-dimensional. And I saw this one in 2002 somewhere in University of California. They showed this one. This is around 200 microns, 200 into 10 to the power minus 6 meters. And this gear system was operational. Okay, they demonstrated this gear system. Okay, so this is, I told 200 microns. So this is a NEMS, nano electromechanical based gear system. Okay, this has many applications they have demonstrated. Now, if the same system, if I go to nano or pico scale, this can be done through atoms, individual atoms. Then can you imagine there will be no friction, zero. Okay, so this is what this is not realized yet. Maybe one day we can realize, but however, this is simulated through modeled through nanomechanical device. A nanomechanical device modeled using about 15,000 362 342 atom. That's the person who designed this mentioned. Okay, so this is what the next generation sensor systems individual. So this they can simulate individually. Then you can put it together, integrate. So the same as semiconductor technology started with the individual transistor to integration to various types of amplifiers, like this way they integrated all in one. So like these shafts and these things, wheels put together, then you can integrate. That is where NEMS, nano electromechanical systems. So this is a transistor, nothing to worry about it. So some of the nanotechnology is already there. Like this is a technology is called I don't know how many of you I don't know your background. So typical atomic force microscope. This is the one microscope regularly used in research laboratories in other places as well. The tip dimension is about 5 nanometers. So this is used to measure the surface profile of material. See, you can say take a glass. Glass, you feel it is very plain. I think the smoothest surface you can see is glass, but still at this scale you can see the roughness on the glass. So this tip is about 5 nanometers. Okay, so here's a laser. This scans through the surface of the material. There is the cantilever will move up and down. There is a laser pointer. The beam is coming. It is deflected because of this movement. This is a nanotechnology based instrumentation that is already there. Now the challenge here is how to make this nano structure. That is very important, because see how to see like silicon technology in 1970s, they started semiconductor fabs where you can make thousands of transistors simultaneous at one shot. So that's all called wafer fabrication process. Okay, like that, how to make these nanostructures. You to make the nanotechnology, first you need to make the nanostructures, then characterize all this. What are the special properties? Then nanostructures based devices. Once these devices are made for a certain function, say this application, that means the functionality of the device you define and make it and test it. After that, you need to package it. Then only the device can be used. So then it becomes a nanotech, NEMS or whatever it is, nanotechnology based device. First, to make nanostructures is challenging. That is where we look at, because the semiconductor technology is well established. Is it possible or to develop similar type of wafer fabrication at the nanoscale? That's what the future vision is, and it's already almost there. Okay, many countries have already reached that level, and such transistors are also being made. Okay, so transistor with a gate length of 10 nanometers is already available. IBM and Intel, they already started manufacturing. So micro nano fabrication is the process of making functional electronic, optical, physico-chemical structures with desired patterns having minimum dimension at nanoscale. This is where, okay, methods so far used to fabricate nanostructures. Okay, there are two approaches. It has been proposed. One is the top-down approach and the bottom-up approach. So, see, research is one side. Another one is the technology development. So, the research also will go up to the technology demonstration and technology perspective, whether it can be done or not, in the limitation. Then the industry will take the technology into a mass production. So, this is the gap still existing. Once that is sorted out, I think that will be handy. So, use top-down approach uses various lithography techniques to pattern nanostructure. The bottom-up approach uses interaction between molecules or colloidal particles to assemble discrete nanoscale structures in 2 and 3 dimensions. This is very important development in this area, because top-down approach is the one where the lithography techniques were used, and that was limited to semiconductor technology. Now this has been changed, and this another techniques. So chemical methods were developed to make these nanostructures And this is an interesting development because no need to go for lithography technique. That's because lithography technique is a semiconductor wafer fabrication is very expensive. I think you might have seen in the newspapers recently, the governments are giving a lot of opportunities for the wafer fab industries to invest in India. Recently, Vedanta and Foxconn, they all approach the government. There is about 76,000 crores incentive given to this. See, you see, last already so 50, 60 years now, this technology has been established, but still India is not been able to make IC chips. Okay, we are not making, we are all importing. Though we are a big market in the world, we are not able to make these integrated circuit chips. Okay, IC silicon-based chips. So hopefully, if this is successful, still a lot of MOUs are going on. I don't know whether it is possible in near future. Then that is a full lithography-based technique. Okay, so they are also not going for CMOS-based chips or the memory devices or the processors, but they are going still. They are making on integrate this one, optoelectronics devices. Okay, at least that we should be able to do it. Okay, so this is where lithography and particle beam lithography. I don't know anybody is having some background in this area. I think in undergrads or physics courses also, maybe a little bit on photolithography and this lithography. If anybody has studied a little bit of nanotechnology courses, they may be having these ideas. I don't know where to target because I'm not able to see the faces here. So maybe I will just scan through. The microelectronics industry has developed a sophisticated infrastructure for patterning nanoscale features by conventional lithography. There are two dominant methods, photolithography. Okay, photolithography is nothing but is a pattern transfer. Okay, see, if you look at this, I've collected from somewhere, Greek, it's a Greek word, litho meaning stone, graphia means writing. That means you will be writing some information on a stone. So in this semiconductor lithography, it is silicon is your stone, and patterns are written with a light sensitive polymer, that is writing. So this is how it is done. So lithographic patterns repeated up to 40 times. This is a way of the technology is developed. I'm not going to the full details. This is separate talk altogether if you go on the just lithography. Historically, advances in lithography have gated advances IC cost and performance. This is very important. The advance, this historically the lithography, the very great advantage. You see, ICs are made. That's the cost, unless until it is done is with using this technique, making an individual transistor assembly is very, very expensive. Okay, so and it needs a very higher and clean room. They're all expensive. That's why industries are not in India very difficult to maintain such fabs, fabrication labs, as well as the higher end equipment. Okay, so whatever it is, this is how it is done. So I don't know how many of you remember these what are the cyclostyle machines. Okay, lithography is nothing but like when we were at high school level, any notice or the multiple copies have to be made. They used to make this stencil cuts. That means they take a paper, the letters are cut, the letters, the alphabets are cut on the paper, then the paper is put onto a printer, then the printer put the inks on it. So multiple copies. So lithography is also same. So almost, okay, it's a print or the artwork on a paper, another suitable material. So in nanolithography is the next level, the branch of nanotechnology concerned with the study of application of fabricating nanometer scale structures. Okay, so and patterns with at least one lateral dimension between the sides. You see, when I talk about the dimension, you see here lateral, vertical. See, dimension reduction can be in all the three axes: x-axis, y-axis, z-axis. Okay, I'm talking about the lateral. So, and the two axes only. I'm not going in the three axes. So, during nanolithography is used during the fabrication of leading and semiconductor integrated circuits, nanocircuitry or nano electromechanical systems. So, and there are varieties of lithography techniques, contact imprinting, different use, industries are using different techniques. So here, I am not going to the details. If here, let us start with this point. Here, you see, this is a silicon substrate, it's a wafer, and you put a photoresist here, and here is a mask. Whatever the pattern you want to make, you make on a mask. In this mask, this is the black is a region. It is not trans. This is the opaque. Opaque means light cannot pass through. This is the pattern where the light can pass through. So this is a light sensitive material, and you put a UV light, then the pattern is transferred on this material. Okay. Then this photoresist can be removed using chemical. So this is a positive and negative photoresist. You can make the patterns. Okay. Photo mask. Okay, like this one, the bright field and the dark field mask you can make, and you can transfer the pattern like this. Okay. So this is done. Then there are so various processes to develop all these things, and to do all this. So it may be too difficult to explain in a short note, this one period. Semiconductor processing, okay, wafer, bake it, align the mask, develop, etch, okay, cleaning, all these things. Now, if you look at this one, this is how an individual transistor is done. I think at least in the masters, this one you can see the P-type semiconductors, N-type semiconductors, transistors. So this is a, okay, NMOS, and this is the CMOS. So this is how the microstructure, not full nanostructure. Nano is up to 500 nanometers. People are doing this one, even 500 nanometer. That means 0.5 microns. 1 micron is 500 nanometers, the 0.5 microns. So this is how the pattern can be transferred. Ultimately, this is the IC chip. Okay, you can see that the bottom. Okay, now if you look at one of the, this is IBM structure or semiconductor processing, complex multi-layer structures are created using multi-level lithographic processing. So this, you can see the cross-sectional view of the whole microelectronic process is done on a silicon. In a silicon, what is done is a semiconductor, a metal for contact, a resistance, and a capacitor. You put all these together, you can make varieties of electronics devices like a amplifier and power supplies, power transistors, all can be built on this. Okay, so this is how ultimately it is done. You can look at the processor semiconductor wafer. So this is a 8-inch wafer, as a 12-inch wafer. Why I'm talking about all these things is, so in India we don't have this. Okay, we don't see to tell you openly. Though I have done a PhD in semiconductor physics in 1990s. Okay, I did this PhD in semiconductor physics, but I never seen a silicon. Okay, so that's what the state of our country at that time. I have never seen a silicon, but I have seen silicon first time when I went to Singapore in 1993. This time the industries were only making 6 inches wafer based ICs. Okay, so this as you can see individually, I have some. This is a like individual chip. You see one. See if you look at the previous one, this is a 12 inches wafer, and this is a person inside the clean room who did all the processing. If you hear about thousands of individual IC chips, later they will cut into the small chip. This is the individual chip. Okay, so this is a 45 nanometer technology they are talking. In this single chip, there may be 100,000 or 1 million, maybe 10 lakhs of transistors put together in one of these chips. Okay, I'm talking about. So why the cost will be reduced drastically means all this entire wafer, the process is done simultaneously. So each chip may be having 1 million transistor. Okay, small one. See, this square is a one chip. Later they cut it into, it's called dicing. So this is the individual chip. Then they package it. Okay, so that becomes an IC. Okay, so this is how the microtechnology and nanotechnology in terms of scaling in nanoscale, the same technology is used, but still there are some limitations below 500 nanometer or 100 nanometers. Then another technique there, technology, another technique-based technology is developed. Okay. Now, apart from these simple structures, varieties of other structures also can be fabricated using lithography. This is a micro needle. Some of these we have done in IASC. Okay, this is a rectangular, the square rod. This is a micro needle. Okay, this is also micro needle for drug delivery. So similarly, like if you look at this one, how many of you have seen your mobile cameras? See, this is a micro lens. Okay, see, all your mobile phones have the cameras, and you look at the backside. There's a small hole. There's a micro lens sitting where this micro lens is done. So this is a well-matured technology, because some of these, I think I have some lenses, because my master's student who did my MTech project with me, who joined this, that time it was just started, 2002, these mobile phones started getting cameras, okay, almost 20 years back. Now they are, see, our old film cameras are completely disappeared. We all live with this cameras, these mobile phones. We cannot spend even half an hour, 1 hour without a mobile camera and the photo. Every 1 hour we'll take one photo at least. So these are the lenses, micro lenses, and this also, when I talk about the lens, it is always a focal length changing. So this is a variable focal length, lens. You can see the focal length is continuously changing, and this is well established technology today. You have this, the dimension of these cameras are even less than a millimeter. Can you imagine? Less than a millimeter. And you can, the higher end mobile phones having the cameras even 0.5, 0.1 millimeter dia. Maybe it is having a wide angle. You can almost cover the entire 270 degrees of angle. Okay, so that is the level of micro nanotechnology. And okay, this you forget. Okay, these are the communication related optoelectronics devices. I think we did it long back, and these structures, maybe I can just glance through how you look at this. Is the optical fiber. Okay, and switching this is the another fiber, the waveguide. You can switch from this to this. You can see now here this optical fiber is connected to this fiber. Now I want to process it. The image signal processing, I can switch over to other channel by changing this one. Now this is connected to these two optical channels. So this is how all can be done through micro nanotechnology. These are all fabricated, done. Okay, MEMS based optical switches. Okay, so these are all West micro mirror. They are all, you see, this is semiconductor based technology, micro nano, micro mirrors, how they are used, the sensors, okay, varieties of structures. I'm not going through all these things, varieties of method. Now, the limitation with this micro technology is the lithography. Lithography is done using a UV light. So when the light passes through a small hole, there will be diffraction. So if I want to make 1 micron or 500 nanometer or 100 nanometer, I cannot use the laser-based lithography technique. I have to go for some other technology. Okay, that is deep UV, or the electromagnetic spectrum. If you look at this one, this is visible. Infrared, longer wavelengths on the right side. Ultraviolet. Okay, deep UV, you can generate the light up to deep UV. After this one, you cannot, because these are the X-rays. X-ray cannot be used. So people have tried X-ray lithography also, but it has other hazardous problems. So once you cross this 150 nanometer, you have a problem. You cannot go with the optical lithography. You have to go electron beam lithography. That is the one that makes the, they have to make the nanostructures, nano devices, that is through lithography. So there is a limitation up to maybe 500 nanometer. You cannot go with the conventional lithography. You have to go for other technique that's called electron beam lithography to make the nanostructures. Okay, let us skip all this one. Okay. Now why I'm telling, okay, some Kannada is also there. Those who can enjoy. I used to give these talks in Kannada as well. So I just mentioned when the light passes through, it gets diffracted. Now, if I do the lithography using this one, if I go to 500 nanometer, my light gets diffracted because the basic physics. So I cannot get the targeted. This maybe 1 mm I can be okay. Sorry, 1 micron, 500 nanometers. If I still this gets diffracted like this, the pattern cannot be transferred with the same dimension. So nothing to worry. So these are all the mask fabrication and other technologies. I'm just talking mainly on the technologies. They're very higher end equipment. None of them are done in India. You need to import all these things. And that's why we are not able to make much progress in semiconductor based or nanotechnology, which is based on the conventional microtechnology industries. So that's what the limitation lies in. Now, this is the X-ray lithography, but people are not using. So limitations are here. Now, another approach is particle beam lithography. So that means instead of the light, use the particles. That is electrons. Now this cathode ray tube based TVs are no more. The electrons in the cathode ray tubes used to move the electron beam inside the cathode ray tube. They produce the image on the screen. That was the earlier TV technology. Now this no more. We are working on the LED based light emitting diodes. That's another interesting photonics technology. Now OLED based screens are there. Flat TVs have come. So before that, this is where the Feynman, one of the top physicists, theoretical physicists, he mentioned that there's a still chance in 1959 he mentioned this one. A challenge. He put a challenge to print a book in a page, book page in an area of 200 times 25,000 smaller than the standard print size. So one of his students, he wrote the encyclopedia in Charles Dickens' Tale of Two Cities in a 6 micron square area. So 6 micron square area, he put the entire this one. That means a lot of chance. There's a plenty of room at the bottom. That's what his indications that you cannot go below the micron structure. Okay, so that's where the next stage of this nanotechnology started. That's electron beam lithography. Here, instead of using the light, people started using the electron beams because the dimension of electron. Okay, I talked about the 0.1 angstrom, 0.0001 nanometer. So this electrons still, atom size is that much. The electron beam lithography, you generate the electron beam and start writing the structures, make the structures using electron beam lithography. So like optical lithography, E-beam lithography, high speed with a small complex pattern is possible. Point by point exposure limits the throughput, parallel exposure, entire field exposure at once. Okay, light diffraction limits. This is where I mentioned on the left side. On the right side, you can go up to a few nanometers. Widely used in R&D. This is used in inventory environment. Now it is slowly going to industry as well. So these are the structures you can write. This is a very higher end instrumentation. It is there. In India, it is so many instruments. All are imported, are available. You can really write smaller patterns using this. Okay. Anyhow, this is a very complicated methodology. I'm not going to explain all this. Varieties of structures can be written using this one. This is how it works. Okay. There are many limitations and many control systems you have to use. And these are the mathematical limitations. See, you can look at these are all the photonic crystals, the cantilevers is all. This is our work only. The diameter of these small holes are about 200 nanometers. Okay. See varieties of structures you can make using this. And imagine a semiconductor optical lithography that you can do in a maybe 1 hour or 2 hours process. The same thing with an individual device, it will take 8 to 10 hours using this optical this electron beam lithography. So it is not good. However, these kind of structures like this, one of my friends from US is very good in beam lithography, has made this critical, interesting structure on a silicon. I don't know how he did it. He didn't explain, but he used to say that he can move these creatures on a silicon wafer. And you need to see this one in electron beam, electron microscope. Okay, I didn't see that, but he proved it. Okay, now another focused ion beam, varieties of techniques are available. They are all very expensive and very difficult to make. And another, the atomic force microscope technology can be used to write these structures. It is very, very much similar to this flowing. Okay, the tip is pulling on the surface. You can do that one. Okay, see, these kind of structures can be patterned. Now, I just talk something on bottom of technology, these methods, So these are all the very higher end pattern transfer technologies for making nanostructures and nano devices. So unless until you master all this, you cannot make technology development, and you cannot deploy that one in the real application. So there are varieties of other methods. This is the advantage with nanotechnology. Okay, sol gel, it's a simple chemical method. PECVD, LPCVD, okay, PLD, hydrothermal method, various chemical reaction methods. These are all available to make this nanostructure. Okay, like chemists have found different techniques. Self-assembly refers to the spontaneous formation of discrete nanometer size units from simplest subunits of building blocks. Okay, these are the chemistry process. You like a crystal growing. You put a one base seed material into it, then use thermal or other annealing techniques so that the structure grows on it. So these are all possible, and this is one of our techniques. We made such patterns using chemical approach, and see somewhere it is applied in biochemistry or biological and medical applications. Silver nano triangles used done through photospace technology. Now, one of the applications which we were using is in the solar energy. See, the solar, how the solar energy is converted into electrical energy. And so the photovoltaics. This is where we also used to work. Now we thought of introducing nanotechnology in photovoltaics to increase the efficiency of the solar cell. Why? Because you know that okay, in nature you might have seen some of the fly's eye, the insects, the mosquito. This is the SEM image of the eye of a fly here. You can see at this corner. Okay, and if you still magnify, you can see this one. What it's a this is a nano lens. That way, nano lens. Why? Because they like even mosquitoes can identify you even in the dark where you are sleeping and which portion of your body is exposed. Okay, they come there only and bite, because there are various explanations, because they detect some kind of infrared emission from your body, directly, then come that side. So infrared is a radiation. So how much radiation? So these micro lenses, they are using a single photon kind of light. They are trapped inside. Maybe that may be one of the reasons. Is it possible to make some structures, and is it possible to introduce that one in a solar cell? In a solar cell, what is to be done is, whatever the light comes from the sun, you need to fully utilize it for energy conversion, or the electrical energy conversion. So that is not happening. See, today's the solar cell conversion efficiencies, silicon is a maximum around 14 or 15%, not more than that. Okay, and there are so many solar cells, perovskite, this and that one people are proposing, but they are not come up to the technology development level. Still, they are still under development, but silicon is well established. The efficiency is less. So, is it possible to trap all the light which comes to solar cell? That's what our idea was. So, this is the theory we just model. instead of using this is a normal solar cell structure, and we made a similar structure like this fly's eye, and we just curved it, and we made these things. Okay, initially we modeled using mathematics. Then we saw there is a increase in efficiency from 25% to 45% when we introduced this nanostructure in the solar cell. Okay, that we fabricated using different method. When we made these structures, you look at this portion is without a nanostructure, with the nanostructure, this is the with nanostructure. So this is the planar. The red one is structure. So if you look at the quantum efficiency has changed from around 20 to 40%. So broadband enhancement in the external quantum efficiency up to 47% improvement in the forecurrent in the best case. That's what we observed. That means you look at the way this is the mathematical modeling we did. So what is happening is whatever the light comes to the solar cell, that is trapped. Okay, this color shows the solar spectrum. All the light cannot get escaped, so that they are trapped inside, so that they generate more photocurrent. So this is how the nanotechnology is being used in solar cells. These are the different numbers I'm giving. So similarly, you can make different types of nanostructures. Like this is by chemical method. So this is entirely different. It is called a hydrothermal method. You just keep some chemicals and hot plate and leave it for some time with the process. We have done some mathematical modeling for this one. This is a hydrothermal method. By controlling various parameters, you can generate different type of structures. Okay, so growth parameters. Okay, distilled water plus H2O2. Various chemicals. So I'm not going to the details. It's entirely separate material. Now, one more thing is we came out with a simple growth technique. This look at the hot plate, and this is a substrate. You are keeping CZTS hot plate techniques for CH8 heterojunction solar cells. So just this is very, very simple, and we are able to make nanostructures. Just controlling the stoichiometry of the chemicals inside. We got various nanostructures. Okay, so you can see here. Okay, same type of chemical with a process parameter control. These are the nanorods to nanotubes, and the tubes are getting opened and you further increase this one. Okay, so this is a ZNO nanostructures formation versus variation of precursor concentration. So this is how a simple technique is can be developed to use. That's why it is more multidisciplinary, and anybody with the motivation to develop and understand the nanotechnology and nanomaterials development can work on this. So now nanotechnology, see, these things, opportunities, new frontier, opening areas, technology development, product development, basic research, all have to be put together if really a nanotech science or nanotechnology based product has to come. So there's a, so in all other areas also it is like this, unless until you have interdisciplinary work, it is very difficult to bring any technology. So in this area there are interesting things happening. So high impact research has to come with this. Okay, major opportunities are here. Industrial partnership has to come, and the commercial potential. So they are all interrelated. If this is done, then the nanotechnology has a big future, and it's already there. People are being used. Now, I think, see, I showed in the previous case somewhere, the nanotechnology is a multidisciplinary science, like one of the art section where you have a multidisciplinary art. So one of the things which I observed was the costumes they used for makeup. They're all nanotechnology based powders. Okay. So this I saw somewhere, and it was there for a long time. Okay. So like that nanotechnology was there for many, many years. Like the goldsmiths used to make gold nanoparticle. They were never knowing that that was a nanoparticle, but it was there. They used to make the nano around the gold. The this precious is metal. So different colors they used to see, but they never thought it's a nanotechnology. But today it is known because we have sophisticated instrumentation. We can measure the dimension. We can actually see what it is. I think that's how nanotechnology is going up. Now, what we can take is very challenging. Front-end technology, back-end technology, system development, bottom-up, which is, see why I'm talking, see, lithography-based higher-end fabrication technique are still a question mark in India, may come or may not come. If the government is fully supporting, inviting industries, maybe next 4 or 5 years we can see. Otherwise, we don't know. Maybe bottom-up approach, system-level development, and the front end difficult, back end maybe packaging. These are the things we can do. I think we are good in that now with the mobile phone. Many frontier handphone companies are investing in India for packaging. Okay, so the inside things will come from them only, because we have put a benchmark that if anything making, we always cheat. That's what the international image is. So that has to go. We should be open. Now, I think I will stop here. So this is how the nanotechnology is. The expectations surrounding nanotechnology, nanofabrication are very high. The governments, companies around the world are spending billions of dollars on research and technology development. So it covers many areas, but one key method is the nanofabrication technique challenge to be addressed. New products are coming, no microelectron, but still requiring nanoscale fabrication. There are many opportunities for the industries to explore. I think it is there already. Okay, how many conventional and unconventional techniques? And somebody will come up. Okay, there's a cost-effective technique to do this one. These lithography limits have to be removed. And some way, we don't know, suddenly some new technology may come, it can take over all these things. However, it has a good opportunity for anybody to work on. Hope we'll see a lot of technologies. Okay, these publications. I think this is 1 hour 5 minutes. I think I have the time I'm given is that much. Hope all are there. If you have any questions, you can.
Yes, sir. Thank you very much, sir. Any questions? Jyoti ma'am, any question from students? Dinesh sir. Ma'am, you can unmute and you can talk with sir, ma'am. I made you co-host. Okay.
Madam, our students will going to ask the questions.
Yes, ma'am. Sir, you can stop this sharing, sir, so that they can see you.
Hello.
Sir, stop screen sharing, sir.
Okay.
Now they can see you. Okay, ma'am, you can ask the questions.
Hello.
Hello.
Sir, cosmetics ಅಲ್ಲಿ nanomaterials ನ ಯೂಸ್ ಮಾಡೋದ್ರಿಂದ ಪ್ರಾಬ್ಲಮ್ ಇಲ್ವಾ ಸರ್?
ಇದೆ ಅದು ಸಿ there are some studies, ಇವಾಗ ಕಾಸ್ಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ ಐ ಥಿಂಕ್ ಬ್ಯೂಟಿ ಪಾರ್ಲರ್ಗೆ ಹೋದವರೆಲ್ಲ ತುಂಬಾ ಜನ ಅದು ಇದು ಸ್ಕಿನ್ ಪ್ರಾಬ್ಲಮ್ ಆದವ್ರು ಇದ್ದಾರೆ. ಅದಕ್ಕೆ ಐ ಥಿಂಕ್ there is you can see some books written on that one. Okay, adverse effects of the nanoparticles on the face. Medical book ನಾನು ನೋಡಿದ್ದೇನೆ ಅದನ್ನ. ನನಗೆ ಗೊತ್ತಿರೋರೆ I think they went for some laser treatment and many other things. Definitely ಇದೆ.
Thank you, sir. What is the National Nanotechnology Initiative?
Can you repeat?
What is the National Nanotechnology Initiative?
Oh, it is there now. Last 2005 ಇಂದ ಸ್ಟಾರ್ಟ್ ಆಗಿದೆ ನ್ಯಾನೋ ಇನಿಷಿಯೇಟಿವ್ ಅಂತ. ಆಲ್ರೆಡಿ ಇದರಿಂದ ತುಂಬಾ ಡೆವಲಪ್ಮೆಂಟ್ ಆಗಿದೆ. ಸೊ ಐ ಥಿಂಕ್ ನಾನು ಅಬ್ರಾಡ್ ಇಂದ ವಾಪಸ್ ಬಂದಿರುವಾಗಲೇ ಶುರುವಾಗಿತ್ತು, ನಾನು ಅದಕ್ಕೆ ಬಂದಿದ್ದು. ಸೊ ಐ ರಿಟರ್ನ್ಡ್ ಟು ಇಂಡಿಯಾ ಇನ್ 2007. That time itself Nano Initiative started, and still we are getting funds from the government, and the governments are also funding industries, a lot of startups coming. So it is there. Country is doing, I don't say very well, but it is doing well. Okay, we have been recognized in the international arena that India is also doing a lot of nanotechnology.
Excellent. And Dr. Jyoti from Chintamani College, sir. Hello.
Hello.
Sir, our students are doing project work and they are preparing nano materials. But they don't have exposure in the fabrication level. So if you have any, will you give any facility or training from ASC for our students so that they can
you can see we have
product in fabricating them?
We have a big facility at IASC, and we have a program for the colleges students and all. That means they can apply and come see. You want nanotechnology, if you want to do it, you should know what you want to do, and you see how to specify what you want to do. Or before doing it also, you can take somebody's guidance so that we can help.
As a project work, they are preparing nano materials.
You see, that's what you do your project in your place only. Okay, and you define what they are doing, whether they are doing a nano. Let's see, definitely a nanomaterial. They are using different method, maybe chemical or green synthesis, varieties of methods. Okay, so a lot of people do from across the state, country, and they use different facilities of like IIT Bombay, IASC, and now there is one. iSTEM is the one, you can note it down. iSTEM is the one. It's a government started facility. Indian some under nanotechnology mission. You go to iSTEM and you can search wherever you are there. You can search which facility is available where. Everything is available there. You can just go.
Sir, one more thing is there any database to check the novelty of the compound what we have prepared?
No, that is there everywhere. You Google, so you can search, novelty. See, you can go to all research journals, and these days all are available online. You can search. Okay, you give the name of your material and see there are hundreds of literature you can see.
There is no separate database like.
No, it is there. Separate. You just Google it. Okay.
Oh.
You can just narrow it down. What you want, you can get.
Oh, thank you, sir.
Okay.
Any more questions? You can check in chat box.
Okay.
Someone asked nanotechnology का main motive क्या है? In chat box, sir. Main motivation of nanotechnology. What is the main motivation?
Nanotechnology is, the main technology is miniaturization. See, isn't it? See, you have a laptop now. You have a mobile. In the same mobile, you want so many things to be done, isn't it? That's what the motivation. Include everything in one. Okay, and the highest memory.
Hmm.
You can now you have a limitation with the memory. You can do all these things. That's the motivation. Okay.
Yes, sir. Okay, almost no questions in the chat box, sir. So we can end here. If any questions, you can raise your hand, or else we can ending here. Okay. Divya?
Yes,
Yes.
madam.
Okay.
Yes, good afternoon, everyone.
1 minute, Divya. Sir, it's
Okay,
time
ma'am.
to say bye to you. Vote of thanks from Divya.
Okay.
Good afternoon, everyone. A special thank to our esteemed speaker. Their expertise in nanomaterials and their engaging presentation style have provided us with valuable insights into their cutting-edge field. We are truly fortunate to have the opportunity to learn from such a distinguished expert. Thank you very much, sir.
Thank you. Thank you all.
Thank you all the participants for your time and